Okay, so we are recording now, and we're starting to look at the problem 2 of the Physics 2 recommended FRQs. I sent you the packet of the problems as well as the packet of the solutions scoring guidelines, and we'll take a look at what they have treated us with. Here's the circuit. I'll draw it. It's not very complicated, but a little easier to look at than looking at the piece of paper. You have a EMF, some kind of power source. We have over here, they draw it as a light bulb, like an actual physical light bulb. I'm not going to do that. I'm just going to do it like this. So we got a light bulb here, and they call this light bulb 1. And then they have here a branch that has a light bulb there. And then we have an open switch. Over here we have a light bulb. And this has a closed switch. And we bring this whole thing back over here to our EMF. And there we go. And this is 1. This top is 3. And this is 2. Okay. And they're giving us some information here. They're saying a battery of EMF epsilon, so potential difference here, epsilon delta V, and for our purposes the same. It has negligible internal resistance, so we're not going to worry about the fact that there's actually a little resistor in here. So we're going to assume that. So this is really equal to delta V, right? It's because R is equal to 0, and a good way of thinking about that. We're also going to deal with these light bulbs as being kind of ideal light bulbs, that they have resistance R. And the reason they're going with light bulbs here is just so we can talk about brightness. So, but we could also just talk about a resistor R, resistor R, resistor R, because they're not temperature dependent light bulbs, even though incandescent light bulbs are temperature dependent in terms of their resistance, because when they heat up, they get more resistance. So, but we're ignoring that part. And they're asking us about what's going to happen when we close this switch. And even though I hate this way of looking at things, it's important to be able to address when the AP asks these questions, because they really like the student A says something about physics. Is it right, wrong? How is it right or wrong? And those kind of things. They like asking those questions. So they have a student that makes the prediction when you close that switch. Oh, wait, they didn't even give an explanation. It's just, okay, all right. Bulb 1 will decrease in brightness when the switch is closed. So they take the switch over here, and they close it, and student 1 thinks the brightness is going to agree or disagree with that statement. So let's just kind of look at this and think about this for a minute. When we close this switch, student 1 predicts that the brightness will go down. Why would that student say that? Let's kind of get in their head. I don't know if we should be doing this, but let's just think about it for a second. Why might you be tempted to say that if somebody dares speak on camera?
I mean, you could just assume if there are more light bulbs, the brightness of all of them would decrease.
Right, exactly. So if you've got more light bulbs, it's going to be harder to light all those. You've only got one battery, so they should all get dimmer. That makes kind of sense. So I think that's what they're aiming for. That student 1 might have a misconception in that regard, that because there are more light bulbs attached to the battery, in this case, that the battery would have a harder time lighting all of them. Therefore, light bulb 1 would get dimmer. But let's kind of look at this and think about this and say, well, dimness is another way of, is a marker for amount of current, right? Because the current that flows, the total current right here, right, all flows through this first light bulb. So if the total current goes up, light bulb 1 gets brighter. If the total current goes down, then the brightness goes down. So asking what happens to the brightness is the same as saying what happens to the overall current. Okay, well, our overall current is, of course, delta V divided by R total, right? And in our case, that's the total potential difference. So that would just be epsilon divided by R total. And what happens to the total resistance when we close this switch here? Once we close this switch, what kind of circuit is this? Is this a parallel circuit or is this a series circuit?
Well, overall, it's still a series, but you add in that parallel factor, which would actually decrease the resistance closer to on the right side.
Perfect. So we have a two-part series circuit. Yes, we are series. So the red element is in series with the green element. So the overall resistance initially for the red one had been R, right? Because this one is not part of the circuit really before we close the switch. So initially the resistance had been 2R, right? So initially we had R0 is equal to 2R. That language makes sense. So before we close the switch, the resistance is 2R. But once we close the switch, call it RF, the final resistance, this guy still has R. What's the resistance of two resistors in parallel if they have the same resistance?
R over 2.
R over 2. So this is R over 2 plus R. So we'd have 1.5 R. I like the decimal expression. You could also go 3/2 R if you want to, but I think this is a little easier for me to understand. So maybe a better way of approaching this. Okay, so the resistance overall has decreased. So if the overall resistance has gone down, and because it's on the bottom of Ohm's law, that means I has increased. And we've written it out as an equation. They would like for you to formulate this as a prose statement on the AP exam, but we can put it in words, okay? So once the switch is closed, then the overall resistance of the second circuit element has decreased. This second circuit element has half the resistance now, decreasing the overall resistance of the circuit. Therefore, the total current has increased. All the current flows through the first resistor. Therefore, that resistor, that light bulb, will shine brighter because more current through a light bulb creates a brighter light. Okay? Now, they want you now to go and actually quantify this kind of based on the power statement. So we're looking at the power that's dissipated in here. And there are three equations that we have for power. I'm just going to remind you guys about those. And you should always have kind of all of them in mind. So P equals I delta V is the first one. And we can combine that statement with Ohm's law. So this would be a great example of equations that you should have handy. Those are not on the equation sheet, but you're allowed to have a cheat sheet. It's not a cheat sheet, it's your notes, where you have this equation, I squared R, right? And you also have P is equal to delta V squared divided by R. Okay? So having these handy for you would be helpful. Okay? So let's take a look at our situation. We want to make sure that we only vary one thing in the equation to compare our initial power with our final power. Okay, hang on a second. They're saying the power expended by bulb 1 is P1. Okay, good. So for this case, this guy, I was thinking maybe doing the whole power, but we're just doing the power for the resistor 1. So resistor 1 has a resistance of R and it stays R. So we just need to use an equation that has R as constant, and we have a varying amount of current, right? Makes sense? Current's gone up. So we should probably use this little equation there to be able to compare the two equations. Make sense? Okay. So the current initially is I, okay? So therefore our P0 is just equal to I0 squared times R. There you go. How about the final current? Let's take a look. For the final current, we need to see what's happened to the overall resistance. The overall resistance has dropped from 2R to 1.5R. So therefore, the current has increased. And specifically, current initially had been epsilon divided by 2R, right? And then our final current is equal to epsilon divided by 1.5R. Make sense so far? Okay, I'm going to just ask, is this too easy, too hard, or are we doing the right amount of difficulty right now?
It's fine, but could you move the screen down a little? Thank you.
There we go. Okay, good. So let's take a look what we have here. I0 is epsilon over 2R. IF is epsilon over 1.5R. And now I'm actually going to write this a little bit differently, maybe. That's probably a good idea. This is 3/2, so this is 2/3 times epsilon over R, where this is 1/2 times epsilon over R. Make sense? Just to compare the two? Maybe that's not a good way of doing it. Is that confusing you? Okay, I'm going to pretend you said no. Okay, so P0 is I0 squared times R, and P final is obviously I final squared times R. They call it P1. Power expended by bulb 1 is P1. P1 is that. Good. So P1 is equal to I0 squared. So that would be 1/2 epsilon over R squared times R. Good. So P1 is equal to 1/4 epsilon squared divided by R. One of the R's is canceled. Good. So there's our power before we have closed the circuit. And then over here, we're going to write down the final power. They call it P new, okay? P new is equal to the final current squared, IF squared times R. When we look at this, we square this, we get 4/9. 4/9 times epsilon squared divided by R. Okay, is that making sense?
Yeah.
Is that okay? Okay, I want to challenge you, not bore you, but I also don't want to overwhelm you because it's a little bit schnickely with the squares and all that stuff. You guys okay?
I forgot how you chose which form of the equation of the power equation you decided to use. Like, how did you choose that
Sure.
one?
So we have these three options over here. Okay, we're looking for the power that's dissipated in this resistor. Okay, whoopsie, here's my finger. Oh wait, my finger's not showing. Crap. Let's go kind of do this view for just a second. So we're interested in the power dissipated in this resistor right here. So we could go with the first one, but I delta V is really not a good idea because when we close the switch, the current that flows through here is increased. And of course, the EMF has the delta V, the potential drop across this resistor also has increased. So they both have increased, and that makes the thing a little bit tricky because we would have to calculate the new current and the new potential drop across this resistor. That makes that equation difficult. The third equation, delta V squared over R, it might be also an option here, but potential difference seems to me to be a little bit schnickelig because it's not as intuitive to me as getting directly at the current. Earlier on, when we talked about why does the overall brightness of that first bulb increase, we had Ohm's law written out right here, where I equals delta V over R to get the overall current. And that seems intuitive to me in terms of using that. So that's why I chose this equation and decided, okay, I'll find the values for the current before and after the switch is closed, and I'll use this relationship right here to then compare the two. We could have also done this, but like I said, finding the delta V across the first resistor seems to me to be not as straightforward as finding the current overall in the circuit, and that's why I chose that. So second one is a better option than the third one. Third one could work. The first one seems counterintuitive, especially because then you have to find I and delta V across that resistor, and that seems like, why? Why would we do that? It seems not a good idea. Okay? Okay, so let's come back down over here for our results. So they would like to know how big P nu is compared to P1. So another way of saying that is they want to know the ratio of P nu to P1. And I don't like the notation they're using. Huh? We good? So P nu divided by P1 is what we're looking for effectively. How much has the power increased? So we look at P nu, and that's this thing right here. That's 4/9 epsilon squared divided by R. And down here we have 1/4 epsilon squared divided by R. And if we multiply that out, these things divide that out, the thingamajiggers here cancel, and we get 4/9 divided by 1/4 is 16/9. So we get that the ratio is 16/9. Or another way of saying that is that P nu, oopsie, let's leave the gap here. P nu is equal to 16/9 P1. Is that on screen? It is on screen. Okay.
Wait, where does it ask us to do this?
It says in part A2, derive an expression for the power P nu expended by bulb 1 after the switch is closed in terms of P1. So it's saying how many P1s do we have dissipated then? How much has it increased? How much has the power increased that's being dissipated in the first bulb?
Okay, thanks.
Okay, makes sense?
Yeah.
Okay, so we went through this, and you guys are awesome, but I have a feeling that some of you might be a little bit intimidated by the symbolic nature of this question. So I just want to remind you of a trick that I told you guys, which was, if you're ever like, man, if I only knew the resistance, you know, if I only knew the mass of the cart on the roller coaster, okay, because you feel maybe more comfortable working with numbers, this problem should work the same, coming back to the problem, if you knew the voltage. So if you're like, I'm going to pretend this is 12 volts, and I'm going to pretend this resistance is, well, 18 volts maybe would work at 6 ohms or something. You know, you just choose a number because you're like, if I only knew those resistances, I can knock this out in no time. You know what I mean? To find the power dissipated in this bulb based on knowing those values. As long as you choose numbers that are consistent with the problem, meaning they said R, R, R. So you'd have to be like 6 ohm, 6 ohm, 6 ohm. That's cool. You can't be 6, 3, 5, obviously, right? That doesn't work. But as long as you choose numbers that agree with your original setup, the ratio you find should be the same ratio, because they say it doesn't matter what R is, it doesn't matter what epsilon is. And for you, that might be easier. Just want to remind you of that option. Okay, and there we go on that. I'm going to take a picture, and then we're going to move on. Okay. Picture here. Got it. Okay. I'm going to erase this. Any big plans for the weekend? I'm funny. Just kidding. No, not funny. Sorry. No, just making small talk. Sorry. There we go. There we go. Okay. So let's check. Oh, now they're asking you to use words in part 3. Okay. How does the result of your derivation in part A2 relate to your explanation in part A1? Okay, they're just saying, make a connection now between what you found. So in part A2, we made an argument based on current increasing, right? So current increasing made the light bulb brighter, but what does that mean? Well, it made the light bulb brighter because more current means more power according to the equation P is I squared times R. So it's a proxy. Current increase is a proxy for power increase, which is a proxy for the increase in brightness. Okay, that's kind of a wordy connection statement there. So let's take a look at statement B. Statement B says bulb 2 will decrease in brightness after the switch is closed. So this person is making an argument that this light bulb will be less bright than light bulb 2 before. Okay, is that a correct statement? Do you guys think that's right? Does light bulb 2 get less bright when you close the switch?
Yes.
Yes. Was that Rhea? Okay.
Yeah, that was me.
Was that you? Okay. So Rhea, do you want to justify why you think light bulb 2 gets dimmer when you close the switch? You can say no, or are you thinking?
I'm sorry, my Wi-Fi just died in the middle of what you said.
Oh, okay.
What did you ask?
Rhea, you said light bulb 2 does get dimmer. You agree with this student. Can you explain why?
Oh, so as we close the switch, we turn that element of the circuit into a parallel circuit. And as you said, we can think of like current being the brightness. And when we close the switch, the current is then split off into two branches.
Okay.
And just logically looking at it, the current will be less. But I can give a mathematical justification.
Okay.
If you
So
want.
so I think you worded it out pretty good there. To be.
We also said it's earlier.
Yeah, I think that was pretty good. So you spoke it through. So you said the red element has now has half the resistance, lowering the overall resistance, so the overall current increases, but the current splits in the second part, and therefore this guy gets less current. If we wanted to be a little bit more precise, because I think the trick part here, and Rhea, I think you noticed that the trick is in the aspect where we have one thing increasing, right? And one thing would have a tendency to increase the brightness because there's overall more current, right? But at the same time, there's another factor that tends to decrease the brightness here because the current that we do have splits. So in order to make your argument waterproof, right, you have to make sure that the splitting aspect overpowers the other aspect. You understand what I'm saying, Rhea?
Yeah, I gotcha.
Okay, so can you throw that in there and just make sure that's actually just say it, even though you haven't. I mean, you could use numbers, but by what factor does the current split over here? I mean, splitting kind of implies it already, but what fraction of the current does this resistor get? Half. Okay, so you have to put in another little side note that the overall current does not increase by how much?
Not as much as half.
You know, so it doesn't double.
Or
So as
twice,
long as
yeah.
it doesn't double, we're okay. If the overall current had doubled or more, like let's say the overall current had tripled, right? Then this resistor, who gets half the overall current, would end up with more current than it had before. You understand? Okay, so that is actually a complicated argument because then you have to be like, is it obvious? I mean, we calculated it was 1.5 times more current. So it's less than an increase by 2, but the argument is a little bit complex. Do you guys agree?
Yeah.
Because we have to have that balance. So it's actually a little,
Agreed.
so you could make an easier argument here about the brightness of this guy through the other relationship for power. So Rhea started the argument off the argument of current and arguing P is equal to I squared times R. Good. And we spoke it through, and the argument we just made together would be valid, but you'd have to include the aspect that the half versus 3 halves, right? So it boosts the overall current by 1.5. This guy gets half of that, so it'll have 0.75 the current that it originally had. Therefore, the current is smaller. Okay, so we could say I nu in 2 equals I 0 to times 0.5. Kind of. You guys understand what I'm saying there? Totally valid and a good argument, but it's a little complex. It would be easier if we argued for the power of this guy through what? What's the other equation that comes to mind for power? We kind of talked about those. We only have 3. So if we're not going to use this one because it's too difficult. Are you guys being shy? Are you guys still there? Did I lose you?
We're here.
Delta
Okay.
V over R.
So we delta V squared over R, correct. So delta V squared over R. So the argument would be based on the power of this guy, based on the potential drop across this guy. And this is a lot easier. I think it's an easier argument to make, for me at least, in my mind. Because just qualitatively, when we already talked earlier about the fact that when we close this switch up here, right, the overall current has increased and this guy has gotten brighter. Well, if this guy, the first resistor, has gotten brighter, that means it has a larger potential drop. Do you guys agree?
Yeah.
Okay, but the potential drop here having increased means that this potential drop across this resistor over here has to decrease because the potential drop of this guy and this guy together needs to be still equal to the total potential drop according to Kirchhoff's loop rule. So if we look at this circuit in terms of kind of a loop, right? We're like, yay, let's KLR the crap out of this. Here we go. So we're going to go this way and then go down here and then come back there. We're going to say, okay, the total potential drop that comes through resistor 1 and resistor 2 needs to be equal to the overall potential boost provided by the battery. But that means if this first resistor has a bigger potential drop, then the second one has a lower potential drop, and therefore this light bulb is less bright. I feel that's a little bit easier, but either explanation would be good. Okay, you guys happy then with part B1?
Yeah.
Good. Okay. Justify your thing with the explanation. We kind of did that here. We can do that where it's 0.75 the current, or you can make an argument over the potential. Let's see, where are we on time? We're a little low on time, so I'm just going to maybe look at the last part C. I want to get to part C because the reason I think this is a good problem is because they do bring in the capacitor. And I think that adds to the problem in a way that makes this acceptable for AP Physics C, especially if they then also had like a curve of the charging curve or something like that. Okay, so let's take a look. In part C, they say they're going to replace bulb 3 with a capacitor. Okay, so same circuit, but now what we're going to do is we're going to go over here and we're going to put a capacitor in here. Good. And now this looks like an AP Physics C circuit to me a little bit, especially if we're going to talk about the rate of change or the time constant or something like that. Okay, so we could put a capacitor in there, and now let's see what they ask us. We now have an uncharged capacitor and we close the switch. Okay, let's see what they ask. How does the brightness of bulb 1 compare to the brightness of bulb 2 immediately after the switch is closed? Okay, so what they're going to do here is they're going to ask the question AP Physics 2 style, where they are only asking about right after the switch is closed, and then they ask for a long time later, right? Because this is the whole idea that in AP Physics 2, you're only responsible to know the initial and final states, whereas in AP Physics C, you have to be able to deal with the rate of change, the charging curve, voltage increase curve, discharging curve, that kind of stuff. So right after we close the switch, this capacitor will act as what? An empty,
wire.
an open wire, right? So it basically means that if we close, just a short circuit initially, so we close this thing, that means at that point, this current, right, will flow right through here, and there'll be no current down here. So as you close this switch, this light bulb will go out, okay? And light bulb 1 will do what at that moment? Get brighter, stay the same? So when you close the switch, we said 2 gets dim, yep, and bright, and the 1 gets bright. Benjamin, are you running that through Wi-Fi? Ben?
Yeah.
Are you running that through Wi-Fi?
Nope.
All right. Kids.
Brighter?
Yeah, light bulb 1 gets quite a bit brighter. It now has full access to the voltage, which means it will actually have 4 times, it has twice the voltage it had before, so it'll have 4 times the power. So this would probably blow this thing out, depending on how it's set up, but it's a good chance it might blow up. So that means at that moment, when you close, this guy turns off, and this one gets to twice the brightness. And then, right, as we now let time pass, a lot later, what'll happen to both these light bulbs here? So this one gotten very bright, and this one's turned off. And now, as time passes, what'll happen to the 2 brightnesses?
Won't they be equal eventually?
Yeah, exactly. They'll be equal. And just to make this into an AP Physics C problem, am I on screen now? I am. So you can kind of imagine like the brightness plotted here, right? So if we take the green bulb and the red bulb, before the switch is closed, they're kind of together, right? And then when the switch is closed, right, the green bulb jumps up in brightness and the red bulb jumps down in brightness. Make sense? And then the red bulb will slowly increase to the same level again, and the green bulb will kind of decrease to the same level. Does that make sense? Now, if this was actually not brightness, but power, right, as discussed earlier, this would increase to 4 times the power. So I was kind of running out of space. I'd have to go up to here, and then it would die down to the same level, and they would together asymptotically approach the same brightness, because as time passes, they would once again have the same brightness later on. Okay? Does that make sense? And those are, again, the 2 shapes. You either have, these are exponential decay curves. This is a flipped exponential decay curve, and this is an actual exponential decay curve, but they both together would arrive at the same power level or brightness level sometime later. And good. We explained our answer. I think we're good, and I think we did quite well on this question. There. Okay. All right. So that brings us to the end of the problem. Any questions about the problem, or you guys feel okay about it?
Feel okay.
Feel okay? Okay. Alex, are you raising your hand on purpose, or is it just?
I don't know how to stop it. Oh wait, no, it stopped. Never mind.
Okay, yes, cool. Let's go. Okay, good. Then I will just turn the recording off, and then if you guys want to ask a question, hang on a second. Aufzeichnung beendet.